Welcome to your own channel of Right Funda.
There is a question from Electrostatics. Let's read the question. Two identical small balls, each having a mass m and charge q, when placed on the smooth curved surface of a hemispherical ball of radius r, the balls move, and at equilibrium the line joining the balls is horizontal and the distance between them is capital R, the same as the radius. Then find the charge on each of the ball. Neglect any induced charges on the hemispherical ball. We have to neglect that quantity. So you read the questions, you try solving the problem. You can pause the video and again you can resume the video. Let's discuss the solution of this. How to solve this question, what has been given to us. Okay. So if you see this ball is there. So if the balls are released from this two position here, then they will be repelling each other and they will be moving like this. Okay. Are they moving like this? And the question is given that they are in equilibrium positions like that right now. So as the balls moves, will this wedge on which they are placed or the ball that also moves? Usually when the balls moves, we say that conservation of momentum apply. Yes, we can apply conservation of momentum if the surface is smooth. If it is fixed, then no need to question of moving. But if it is smooth also, bottom surface is smooth also, then also this wedge will not be moving because they are symmetrically there. Both will be repelling each other and center of mass has to rest. So initially both were at the bottommost positions. Then center of mass will be somewhere here and that has to be here. So they will go like this and this wedge will be at rest. So at this position, if I draw the free body diagram of the block, what are the forces that will be acting on the block? One force that will be acting is like this, that I'll call the mg force. One force that will be acting like this, I call the normal reaction. And another force that will be acting is the suppression. This force is the electrostatic repulsion of this charge on this. The three forces that will be acting. So if I write the values on this, then this is Fe, electrostatic force between this and this, they will be repelling each other. And the charge on this equal to Q, charge on this equal to Q. So we can calculate this one. This is my normal reaction and this is my mg. Is there any other force? No, there are no other forces. In the ground reference, the three forces are there. The smooth is given. Had this been rough, that the friction force would have been there, but it's a smooth thing. So if I want to calculate this electrostatic force, that we know the electrostatic force Fe is nothing but q square, q square by distance separation between them is in the question given there r square, the distance. So my electrostatic force is there. So now this is saying that this is the equilibrium position is there. If this is the equilibrium position, then net force must be equal to 0. So I can resolve the n into two component, mg sine theta, mg cos theta. I can write like this and I can equate them, or I can apply Lami's theorem too. So here, if this angle is theta, so this angle will be equal to theta. And from this, we say this is an equilateral triangle. This is an equilateral triangle because this r is given. So this angle will be equal to 30 degrees. So theta is equal to 30 degree. Okay. So this angle is equal to 30 degrees. So I'll write this one. I'll erase this one. I'll write this as the 30 degree. Okay. So if I apply Lami's theorem, I can resolve and equate this equation of motion I can write, but I can resolve this and equate the Lami's theorem directly I can write. So I can write from Lami's theorem Fe by sine of the angle between the other two forces, because the three forces are there and equilibrium, then only Lami's theorem is applicable. So if I see this value, this angle Fe by sine of this angle, this is equal to 180. This whole angle is 180 and this is 30. So this is equal to 180 minus theta. So I'll write this equal to sine of 180 minus 30 must be equal to this mg by the opposite angle of mg is this angle. This is between the n and Fe. N and Fe will see this angle will see this is equal to 90 plus 30. So I can write here is equal to sine of 90 plus 30. So if I simplify this one, then I got this equal to Fe by sine 30 is equal to mg by cos 30. So Fe is got the mg tan theta. I can obtain this. And this is a 30 degree there. So I can write Fe is equal to k q square by r square is equal to mg into tan 30 degree. So in this problem, so I can get this value of q square is equal to mg r square k into root 3. I can put the value of k if I wish. K is equal to 1 by 4 pi epsilon naught. I want to substitute, or I can write q is equal to mg by k root 3 cos square root into r. This is what I obtain if the position, at the equilibrium position, if the distance separation is r, the same as the radius of the hemispherical ball, then the charge must be equal to this much. Okay. Now, once we have solved this problem, now I tell you one homework. You take one homework. If it is given that these balls are there and these balls are very, very small radius r is there. Their radius, each radius is r. Then find out if you release them, similar charges, they repel each other. Then they go like this. So what should be the minimum charges? What should be the minimum charges here so that they can reach up to the top of this, or they will go out of the balls? What should be the minimum what is the minimum charge to be given? So write homework, take a homework and solve it. What should be the minimum charge given to this if their radii are small r, and the small r is less than, very small than capital R, of course, it's less than, much smaller than capital R. So if the radii are smaller and they release from very nearby position here and they release, then what should be the minimum charge on the balls so that they can go out of the balls? Find the minimum charge. So solve this problem, try.